Any guesses on what we're talking about today? Logarithms, yay! Okay, so let's work our way through this introduction to logarithms stuff. Okay, shown as a graph of the exponential function f of x equals 2 to the x. Does that look familiar? Yeah, we just studied it, right? We just finished exponential functions. What's the value of x if the function equals 20? In other words, what exponent can you use on a base of 2 to get an answer of 20? 2 to the x power equals 20. What's x? Well, we may not know how to solve this equation yet, but we can approximate it, can't we? Okay, so let's use my favorite method and guess. We want to guess. Well, 2 to what power equals 20? 2 to the 4th power equals 16, doesn't it? So okay, so what'd you say? 2 to the, why is this not working? Go away. 2 to the 4th power equals 20. 16. And what else do we know? 2 to the 5th power is 32. Excellent. So wait. Do we need any more? What are we trying to get? 20, right? So our answer is going to be what? What were you going to say? So between 4 and 5. Okay? Is it closer to one or the other? Can we say that? Yes? Why is it closer to the 4? As opposed to... Yeah, okay, so 20 is closer to 16 than it is to 32. Is that what you're saying? So it's between 4 and 5, closer to 4. Now the directions on this section says approximate it to the nearest tenth. So what do you want to go with? So you want to say 4 point what? 4.3. Well, it's the tenth, honey. Tenth is 1 decimal place. I am. Okay? All right, then it asks us to use a table. So I'm going to turn my calculator on. I'm going to go to a new document that I don't want to save the old one. And I want my document to be a graph. And I want you to focus, Mr. Calculator. 2 raised to the x power. Now, how do I see the table? Control T. This isn't helping us at all. Because all it's telling us is it's between 4 and 5, and we already know that. But it wants us to approximate it to the nearest hundredth. Do you know how to change the x values on your table? May I show you? Let's go to Menu and choose Table. Look, let's choose Edit Table Settings. So we got to figure out what this means. Where do we want our table to start? 4, okay. How do we want our table to change? If we're trying to get it to go to the hundredth, so point what? Is 0.2 going to change it by the hundredths? 0.01. Very good. Okay. We don't really need to mess with those two, so let's go ahead and just go to OK. So what am I looking for in my table? 20 where? In the y value. Okay, so I'm going to scroll, and I'm going to scroll, and I'm going to scroll. Whoa! Write down my final table. So I'm going to write down 4.31, 4.32, and 4.33, because that's pretty much where it is, right? We'll say 4.34 just for giggles. There's my x, there's my y. 4.31 is 19.8353. 4.32 is 19.9733. 4.33 is 20.2521. Oops. Don't write that down yet. I wrote down the wrong one. 20.1122. Sorry about that. Why is it yellow? That's better. Keep going. Okay, excellent. On calculator. Okay. So that's pretty close, right? We got to the hundredths. Is that good enough? Well, let's look at the graph. See if we can get any closer. How could we figure out just by the graph? So I'm going to hit Control T to make the table go away. What could I do to figure it out by looking at the graph? Menu? And what? What are we looking for, though, on Analyze? Not the way we have it entered, no. What if I hit Trace? What am I looking for if I hit Trace? I know that's not really nice to trace. That's not what I'm talking about. I'm not talking about him. I'm talking about this graph. The trace function on the calculator. You've never done this? Okay, well, how about if we hit Trace, and what are we going to look for here? If this is my ordered pair down at the bottom, what am I looking for? You see how it's at the point 0, 1 right now? What point am I looking for on the trace function? Something 20, right? So I'm going to use my right arrow to try to find 20. What? Yes, thank you. So this doesn't really help me either. It doesn't get me any more specific, does it? Because I have 4.2 and then I have 4.5. We're already closer on the table, aren't we? Sketch the graph. Well, it's different now than it started off, isn't it? So I'm gonna sketch it just like it is right now, because that's kind of the important one. And this says F1 is 4.5, 22.6. And if I go back one, it's 4.2, 18.4. That doesn't really help me a lot. Okay? Now, somebody else said do menu, analyze graph, and then hit 20. Well, I can't do that because there's no 20 over here. But what if I hit trace and then hit 20? The problem with that is that's entering x as 20. That's not what I want, is it? Okay? So if I hit menu, trace, graph trace, and I hit 4.34, or 4.33 is better, that gets me pretty close. But once again, I already knew that, didn't I? So in this case, does a graph help me out? No. Okay. So is there a way to solve 2 to the x power equals 20 algebraically? Let me give you a hint. Chances are if they're asking you if there's a way, there's a way. Okay? So let's think about this for a second. We need a way to undo exponents. Kind of like we undo these other things. For instance, if we're adding 4, it looks like this. N plus 4 equals A, right? How do we solve for n in this particular equation? We subtract 4 from here and here, right? So we get n equals A minus 4. The way we undid addition was subtraction, or adding negative 4, adding the opposite, right? What about multiplying by 3? This is what it looks like. How do we solve for n? Divide both sides by 3. So it looks like a over 3. We divided by 3. Or what else did we do? How else could we think of it? By 1/3, which is called the what? Reciprocal. Duh. Okay. What's happening right here? It's being square. So we're squaring. How do we undo a square? So if I do that to here and here, I get plus or minus the square root of a, right? So I undid it by square rooting. What else? How else could we think of that based on the chapter we just finished? So raising it to the 1/2 power. Very good. So now we come to this one. What if the variable is in the exponent? All of our work has come down to this. If this is what it looks like, here's how we solve for n. What do you think that's called? Yeah. Logarithm. We use a logarithm to undo an exponent. So, because I don't want to leave an empty box, the way to undo exponents is to use, logarithms. Any questions? If I were you, I would have a lot of questions right now, because it's the very first day of logarithms, right? That's okay to have a lot of questions. I'm telling you right now, this is kind of our most important thing of the day today. Okay? We're going to work on it even some more on the back. Okay? What does the graph of a logarithmic function look like? Well, you remember when we talked about quadratics? And right after we talked about quadratics, we talked about square roots. And a lot of the same things that we did in quadratics, we could also do in square roots, but just kind of backwards. And then we talked about cubes, and then we did cube roots right after that. And a lot of the same things that we could do in cubes, we could do in cube roots, except kind of backwards. Do you remember what kind of a relationship those two functions had with each other? Squares and square roots, and then cubes and cube roots. What kind of relationship was that? How were they related to each other? They were. That's exactly right. Okay? They were inverses of each other. But guys, if that's true, if all that stuff is true, and I'm telling you right now that exponential and logarithmic functions are inverses of each other, doesn't that help us out a whole lot? It does, right? How do we find an inverse of any function? How do we find its inverse? Switch x and y. Okay, it's not necessarily opposite. I know what you mean, but that's a little bit of the wrong vocabulary word, and I think you'll see what I mean in a minute. Okay, so how could we generate the logarithmic graph? What'd you just say? Switch x and y. And isn't that super, super handy that we have an exponential table right here? Because couldn't we find the logarithmic table really easily? By how? Okay, so 0.25, 0.5, 1, 2, 4, and 8. They were the y's, now they are the x's. -2, -1, 0, 1, 2, 3. They were the x's, now they are the y's. Is this a table, is this information right here that I could graph? Okay, let's do it. If x is 2.5, y is -2. If x is 0.5, y is negative 1. If x is 1, y is 0. If x is 2, y is 1. If x is 4, y is 2. And if x is 8, y is 3. Is that what you expected the inverse to look like? Yeah? Because what line do inverses reflect over? What did we do with the x and the y? We swapped them? That's not even a word. Switched them. I was trying to say oh, Jiminy Christmas. I was trying to say switch and swap at the same time, I think. Sorry. Didn't we kind of make them equal then? Gave the other one the value? So wouldn't it reflect across this line y equals x? And if I folded this paper right along that line, along the line y equals x, wouldn't these two functions be right on top of each other? It would, right? So that's another way to show that they're inverse functions. Now, the cool part about that is if they're inverse functions, there's a lot of stuff about logarithms that we already know. Now, that's a little bit of foreshadowing because we're not going to do too much of that today. We're going to work on some of that tomorrow. But just a little, adding a little excitement to the story. That's what foreshadowing does, right? Okay. So, this right here is the most important thing that we're going to talk about today and tomorrow and the next day. Okay? This section right here, super, 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 super important because it is the definition of a logarithm. If we don't know the definition, can we even do anything with it? No. So here's what I want you to think about. If b to the x power equals a, that's something you're already familiar with, right? B to the x power equals a. I'm going to show you how to rewrite that as a logarithm. Now, you just told me you would switch x and y, right? So the problem is there's no y. That kind of ruins that, right? But what is an equation like this typically equal to? Isn't it not a but y? So what if I switch these two? Would that be okay? Not really, right? That would leave us still exactly where we were before. I still have my variable and my exponent. So let's think more about kind of switching places. Okay? What is this b called right here? In relation to the exponent, what is it called? It's called the base, right? It's the base of the exponent. It's the thing that's being raised to the power, right? Well, what's really cool is when you write a logarithm, it's right there. And guess what it's called? A base. So the base of the exponent is the base of the logarithm. Oh, geez. So x goes here. And what's that called? What was it called over here? The x. What's that called? So in the logarithm, it's the exponent. Sorry, in the exponent, it's called the exponent. And in logarithmic form, it's called the answer. Right? That's what we're trying to solve for. One more thing. Well, guess what it's called? Yeah, I like to think they were fighting about this. And they couldn't come up with something, so they just decided to call it the argument. I have no idea why it's called the argument. That's what I think of in my head. I think of mathematicians arguing with each other because that's kind of funny. Okay? But over here, it's what you get when you raise something to the power. Here, it's what you're taking when you're taking the logarithm. Okay? So this part is kind of important too. And when I mean kind of, or when I say kind of, I mean really, really important. Okay? How do you read this? How do you read this sentence right here? Well, here's the deal. I always said it one way. I'd only ever heard it said one way. And then I met a really, really smart girl. And I said it, and she was like, that's not the way I've said it. And I said, well, how have you said it? And she told me the way she said it. And after discussing it, we decided both of them make sense. We decided not to have an argument. But I want you to know that there's two possible ways that this can be said. I'm most likely going to say it the way I've always learned it, just for the record. But the other way is not wrong. Okay? Here's how I will say it. Log base b of a equals x. Log base b of a equals x. Any guesses on what the other way that you could say it is? Okay, so you're just switching those two around. That's okay. But what I meant is more like this. Log of a base b equals x. Does that make sense? It doesn't matter which way you say it. Log base b of a equals x is the way I typically say it because that's just left to right. Does that make sense? Okay. Why do we use them? Yeah. Okay. Do you mind if I say it just a little bit different for us to write it down? To get the variable out of the exponent. That was our problem with the first problem we worked on today, right? The 2 to the x equals 20. I couldn't solve it because my variable was in the exponent. Now we know a way to get the variables out of the exponent. We use logarithms. Before we can start the glamorous solving equations of logarithms and doing word problems with logarithms, which are one of my favorite things to talk about. You'll see why when we get there. It's super exciting. We have to be able to kind of manipulate them first. I don't mean like the bad way of manipulation. Like we're not going to try to make it wear makeup when we don't think it needs to wear makeup or something like that. Okay? But we need to talk about how to change something from exponential form into logarithmic form. And I need to be able to give you a problem in logarithmic form and you change it back to exponential form. Any questions about that? So let's do a couple of these. If I start in logarithmic form with 7 squared equals 49, the first thing I want you to notice about that sentence is that it's true. 7 squared is 49. Right? So if I'm putting that into logarithmic form, the first thing I write is log. What is its base? What is the base of the exponent over here? 7. So that's the base of the log of 49 equals, what's the exponent? 2. What about b? What do I write first? Log base 3 of 243 equals 5. Log base 6 of 1/36 equals -2. Got it? Okay. Let's go over to h. What is the base of the log? 2, then that needs to be the base of my exponent. What's my answer? X, so that's my exponent. And what's the argument? 64. You get the idea? Okay, we need to talk about some special situations then. Look down at K. Well, I have a problem. What's my problem? I don't have a base. When I don't have a base, well, think about this. If I have X, if I just have a random variable, what's the coefficient in front of that? 1. It's not written. How do you know it? Because it's understood, right? What about the exponent? What's the exponent on this X? How do you know it's not written? It's understood. You just know it, right? That's what's going to happen here. When we have log of 100 and there's no written base, that's called the common log. And the common log uses a base of 10. Ooh. Okay? It's not going to be written. It doesn't have to be written because it's the most common logarithm that is used. Okay? So, how are we going to write it in exponential form? What's the base? 10. What's the answer? 2, then that's the exponent. Equals 100. So the nice part about when all these are actual numbers, when we're just transferring them back and forth from logarithmic to exponential, is that I can actually know if this is right. Is 10 squared equal 100? Yeah, if I did it wrong, it would say something like 2 to the 10th equals 100. Is 2 to the 10th equal 100? Nope. It might say 10 to the 100th equals 2 if I did it wrong. That's definitely not right, is it? So that's a good way to check right there. Okay? Now there's a couple more things I want to talk about before I let you go. Right? One of them is there's a common log, and then there's also something called a natural log. Okay? A natural log uses a base of e. Remember that e that we talked about in exponential form? Okay? That's the same e. When it has a base of e, it says it's called the natural log. But what's interesting about this is that it looks like this. It's an L. Now, this is super confusing to me because I'm mostly logical. Sometimes I'm not, but that's okay. Because it seems like natural log would not be ln. That seems backwards to me, right? But then again, nobody asked me, and that's okay. Okay? log is logarithm. ln is natural logarithm. You okay with that? That just means log base e. All right? One more thing. I want you to look back up here at the graph. Looking back up here at the graph, the exponential graph that we talked about right here, what was its domain? How far left does it go? How far right does it go? All the way, so all real numbers, right? What's the range of this graph, this exponential function? How far down does it go? Almost to 0, but never gets there. So y would be, greater than 0. What is the domain and range of our new logarithmic function? What's its domain? How far left does it go? To 0. Is it ever going to get to 0? No. And how did you know that? Oh, because it's the range of the other one, and you know we switch x and y in our inverse functions, so wouldn't the range of this one be the domain of this one? The only thing I had to change was the variable, right? Awesome, good job. What about the range? All real numbers. Now, could you figure that out just by looking at this? Probably. We've worked on domain and range a lot this year, okay? You may not be able to tell it's gonna go all the way to 0 and not get there, but you know it's going to go this way. But you can definitely tell it's going all the way to the right. What about the range? Can you tell it's going all the way down and all the way up? Yeah. Okay. Any questions about this? Okay, so we're going to start just finishing this up, making sure we can go back and forth between exponential and logarithms. Any questions about that? And we'll start working on other stuff starting tomorrow. Okay? Peace.